Hello everyone, welcome to Vihari Academy. This is Dr. Rekha Piliyodigula, researcher by profession. In this session, we are going to discuss about del operator, and from this we can form gradient, divergence, and curl. So now let us start discussing about del operator. Before this, it is very essential to discuss about divergence of a field. For example, if you have a function f which is completely dependent on the independent variable x, if you want to know how this function varies when we tune x, we have to differentiate it with respect to x. This is called as derivative. This explains us about how fastly this function f is varying when we change x through an infinitesimal distance dx. So for example, if you have a function which varies with respect to three independent variables x, y, z, which are defined in Cartesian coordinate system, then how you can arrive quantifying its variation with respect to these three independent variables x, y, and z. Here we have to invoke the concept of partial derivatives. These partial derivatives, they tell us how rapidly this function f is varying when they are varied through an infinitesimal distance dx, dy, and dz along three coordinate axes. So now let us write derivative of function f. Df in this case will be dou f by dou x along through the infinitesimal displacement happened across x, which is denoted as dx, and dou f by dou y. This is the change happened in function f with respect to y along through the displacement dy along y direction, and dou f by dou z dz along z direction. This term can be splitted into two as a dot product of two vectors. As this change is having direction towards three coordinate axes, we can write this in vectorial form, the variation of function f along three directions. And when the displacement happened through x along x, y, and z directions through an infinite elements dx, dy, and dz. So this can be resulted out from the dot product between these two vectors. This we already discussed in our earlier sessions, that this denotes the infinitesimal displacement happened along x, y, and z directions. So I can write it as di bar, which is the infinitesimal displacement vector, and the remaining term is this one, dou by dou x I cap, and dou by dou y z cap plus dou by dou z k cap and f is a scalar function into di bar. This term is nothing but del operator. As this is in vectorial form, we can represent it as del bar f dot di bar. This whole term, that means del operator acting upon the scalar function f, together is called gradient. So now we arrived to the point of del operator, which is defined as a vectorial form. This is the del operator. When it operates on a scalar field, it is called gradient. So it is very important to understand that del bar is not physically a vector, but arithmetically it can act as in all other ways that any other vector operates. We know the derivative of df when the function f, which is a function of x, y, and z, can be written as del bar of this scalar function f through an infinitesimal displacement vector di bar. Write this term in terms of their magnitude, we can write it as del bar f into the magnitude of di bar cos theta, where theta is an angle between the gradient del bar f and the displacement vector di bar. That means it is simply an angle of inclination between two vectors. Fixing di bar, keeping it as constant, that means moving through an infinitesimal distance, a small distance from the point of consideration in the scalar field f. When it becomes constant, the remaining term is magnitude of gradient of scalar field f and the cos theta. So this is the increment or the variation or that is happening in the scalar field f, scalar function f. That means this df can become maximum when this term is maximum. So stating that df is maximum, let us write the term of magnitude of del cross f cos theta. It can be maximum only when cos theta is 1, which means that when theta is 0 degrees. That means when theta is 0 degree, when theta is 0 degree means that both this gradient of the scalar function and the displacement vector are in the same direction. When they are parallel to each other, we can experience maximum change in the function f. What does it mean by? So now we understood that df can be maximum. That means maximum change in function f happens when the angle between the gradient and the displacement vector is 0 degrees. This means that gradient is always pointed towards the direction of maximal change in the function. So this is what we have to understand from this. So gradient, the direction of gradient will always be pointed towards the direction in which direction the function f is experiencing maximum change. Now let us think about the geometrical representation or the real-time interpretation when this gradient vanishes out. That means if we have occurred a situation where the gradient of scalar function f becomes 0, what does it mean by? The derivative of f is written as the dot product between the gradient and the infinitesimal displacement vector. And here, if in case, which is nothing but this is becoming 0, that means when we moved or when the displacement happened infinitesimally through a displacement vector di bar, there is no change in function f, which means that f is a constant. So at any point, if the gradient is becoming 0, it means that there is no change occurring in the function at that point, which means that at this place, at that point, the point can represent either point of inflection or a saddle point or stationary point. Say for example, we have function f here, and here is the displacement vector di bar. It means that when the gradient becomes 0, the point may be its maximum or at minima, or it may be anywhere where the function is not experiencing any change with respect to the displacement. So if we have to find out any static point or stationary point or maxima or minima or saddle point of a function, then we can keep its gradient as 0. That point will be the saddle point or stationary point. So now we have del operator, which is defined as I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. It is not a vector. Arithmetically, it can act as a vector, but in definition, it is not a vector. It has no meaning until unless some scalar or vector follows it. It is just like an instruction passing in such a way to operate on the following component. It may be scalar or vector. If this del operator acts upon a scalar, we call it as gradient. Say S is the scalar. If it is acting on vector, it can participate in the multiplication in two ways, like through the dot product or cross product. The dot product is called divergence, and if it is if it is the cross product between the del operator and the vector, we can call it as curl. So finally, we have gradient, divergence, and curl. Let us discuss each of these components separately. We have already seen the gradient, and now let us discuss about the divergence. Say for example, we have a vector v bar. If we are operating del operator through dot product, it is called divergence. Arithmetically, it has a meaning of dot product between two vectors. This is a vector and this is a vector 2. So it will lead to the scalar value. What is a divergence in real time? The divergence gives the quantified value of a vector, how it is getting diverted or how much it is diverging from a point. This thing is defined by the divergence. If you take any point in a three-dimensional space, if that point is in a vector field, then the divergence may be 0 or non-zero. If the divergence is 0, then we can call it as a static field. If it has a non-zero divergence, it may have positive or negative divergence. Say for example, here is the point of consideration, and if we have vector field lines passing like this, then the divergence at this point will be positive. So positive divergence at any point represents the source point. For example, if the vector is passing or pointed towards the point, then this point is called a point with negative divergence, which is nothing but a sink. If any point or if any vector field is given, and if they are asking you to find out whether it is a source or sink, then you can find out its divergence, and from that you can make a decision on that whether it is a source or sink. Now let us see curl. Arithmetically, a vector is defined as del bar cross v bar. That means when we operate del operator on a vector through cross product, we can get the curl value. We know that del operator can be written as I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. And if we write v bar as vxi cap plus vyz cap plus vzk cap. Now let us write del bar cross v bar. we can write del bar cross V bar with respect to the cross product between two vectors. First we'll write ijk, and here comes dou by dou x, dou by dou y, dou by dou z, and the second operand is V bar. Here we can write x component, y component and z component of the vector, and we are going to take its modulus, which is nothing but I cap of dou vz by dou y minus dou vy by dou z minus j cap of dou vz by dou x minus dou vx by dou z plus k cap of dou vy by dou x minus dou vy by dou vx by dou y. So this is how we can find out del bar cross V bar. What is its physical interpretation? What does it mean by? Say for example, we have a three-dimensional space and if we have a vector field like this, if we consider any point inside this vectoral field, the curl of this vectoral field gives how much swirling is happening around that point. So this is what del cross V bar means. Finally, we have three parameters with del operator. The first one is gradient of a scalar, divergence of a vector, and curl of a vector. And now let us see how many combinations we can make with these three parameters. First, let us fix gradient and then make combinations with divergence and gradient curl. The first combination that is possible is divergence of gradient of a scalar. The second combination is curl of gradient of a scalar. Then now we'll keep divergence as constant and we'll make combinations with gradient and curl. Gradient of divergence of a vector, and fourth combination is curl of divergence of a vector. Fifth combination we can make by keeping curl as a constant and making combination with gradient as gradient of curl of a vector, and the last combination we can make is divergence of curl of a vector. So this is the divergence of gradient of a scalar. As this is a scalar, we can take it off and we can write as del dot del multiplied by the scalar s. This can form del square s. Here this del square is the Laplacian operator. We call it as Laplacian operator, and this is a scalar operator. Del bar is a vector operator and Laplacian, which is del square, is a Laplacian operator. Sorry, scalar operator. Now let us see the curl of gradient of a scalar. As this is the scalar, we can take it off and we can write the curl term, that is cross product, inside the bracket. We know that this is 0 because a vector cross multiplied by itself is 0. So this term becomes 0. So curl of gradient of a scalar is 0. And gradient of divergence of a vector, this is not equal to the divergence of gradient of scalar. This is very important point we have to remember. And coming to the curl of divergence of a vector, here divergence of a vector is a scalar and we cannot find out, or we cannot cross product a vector with a scalar. So this combination is not at all possible. Next combination, gradient of curl of a vector. If we have a vectoral field in 3-dimensional space, say for example like this, the contour lines will be in YZ frame. The curl will be along the x-axis. That means away from the board. If we apply gradient, if we have to consider gradient, as there will be no contour lines, the gradient of this curl will be 0. That is how this becomes 0. Coming to the divergence of curl of a vector, this is also 0 because calculating curl of a vector around a point, there will be no contour lines or the field lines that are passing through this point. Only when we have a field lines or vectoral field passing through a point, we can calculate its divergence, how much the field is diverging from that point. So there will be no field across the point, so the divergence of curl of a vector will be 0. And what about the second order derivatives? The two possible combinations are divergence of a vector field and curl of a vector field. If you consider this one, this has no physical meaning, as divergence of a vector leads to a scalar product, I mean scalar, and we cannot find out divergence for a scalar field, so that it vanishes out. And coming to this combination, we can expand this term. This we can take in a form of vector triple product between a bar, b bar and c bar, 3 vectors. We can resolve this one through BAC minus CAB rule, which is nothing but b bar of a bar dot c bar minus c bar of a bar dot b bar. If we apply this formula for this one, del cross v, that means curl of a vector can be written as del bar of del bar dot v bar, that means gradient of divergence of a vector minus del bar dot del bar. This is nothing but Laplacian of a vector field. So finally, curl of a vector leads to this one, minus del square V bar. Again, in examination point of view, this is also very important. Most of the questions may be asked from this one. Now in this session, we discussed about gradient, divergence, curl and their combinations. And in the next session, we will talk about integrals. These integrals will be line integral, surface integral and volume integral. And after discussing them, in combination of these three parameters, that means gradient, divergence and curl, how these integrals can be combined together to lead to the different theorems. These things we can discuss in the next session. Thank you.